Good morning, everyone. In the last week, we are covering stoichiometry. So, hoping that you get some important point regarding that. In this week, we are going to revise uh, gaseous state. So, this is also an important topic. Let's revise some important concepts of gaseous state. So today we are going to revise Dalton's law of partial pressure and Graham's law of diffusion. Right? So today we are starting from Dalton's law of partial pressure. That is very important topic. Dalton's law of partial pressure. The first thing we should aware about Dalton's law of partial pressure is this is valid for non-reacting gaseous mixture. This is valid for non-reacting gaseous mixture. These gases may be ideal gas or these gases may be real gas, right? So Dalton's law is valid both for ideal gas as well as real gas. Valid for both. How we say that it is valid for real gas? In liquid solution, when both the components A and B, both the components are volatile, right? So they are present in liquid as well as vapor state. So we are writing that the total vapor pressure of the liquid mixture is equal to vapor pressure of component A plus vapor pressure of component B. Since A and B component both are present in liquid as well as vapor state, that's why we can say that this Dalton law is valid for real gas as well as ideal gas. So when we are discussing Dalton's law, suppose we have a container in which there are three non-reacting gases. Let these gases will be A, B and C. The number of moles of gas A in the container is Na. The number of moles of gas B in the container is Nb. The number of moles of gas C in the container is Nc. So now we can write that partial pressure of gas A, it means that when only gas A is present in the container, there is no B and C gas in the container, right? So partial pressure of gas A is equal to number of moles of gas A RT divided by volume of the container. We are using ideal gas equation. Similarly for gas B, we can write number of moles of gas B RT divided by volume of the container. Same way for gas C, we can write number of moles of gas C RT divided by volume of the container. If we want to write that what is the total pressure of this gaseous mixture, then we can write that is equal to total number of moles of gas A plus B plus C into RT divided by volume of the container. So now using these, we can write that P total vapor, total pressure of this gaseous mixture is equal to partial pressure of gas A, partial pressure of gas B, partial pressure of gas C. This is one of the form of Dalton's law, that the total pressure of the system is the sum of partial pressure of all the components present in the system. Similarly, by using, suppose this is equation number 1 and this is equation number 4. This is equation number 2 and 3. So now using equation 1 and 4, I can write that equation 1 divided by equation 4. On the left hand side, we can write partial pressure of gas A divided by P total is equal to number of moles of gas A upon total number of moles, that is Na plus Nb plus Nc, that is mole fraction of gas A. So from here we can write that partial pressure of gas A is equal to mole fraction of gas A into P total. Similarly, we can write that partial pressure of gas B is equal to mole fraction of gas B into P total. Partial pressure of gas C is equal to mole fraction of C into P total. Right? So we can write here that the mole fraction of a gas is equal to partial pressure of the gas divided by total vapor pressure. Right? So we know that if I write here what is the value of XA plus XB plus XC, I am getting that is equal to partial pressure of A, partial pressure of B, partial pressure of C upon P total. And here we are getting the value 1. We already know that there are 3 components. So the sum of mole fraction of all these 3 components is equal to 1. Right? So what is the point we have to remember? Dalton's law of partial pressure will be valid for non-reacting gaseous mixture. That gas may be real or that gas may be ideal. We can write Dalton's law in 2 forms. One is the partial pressure of a gas A is equal to mole fraction of that gas into P total. And the other is that the sum of partial pressure of all the components of a gaseous mixture is equal to the total pressure. Right? Now, while solving the problem, what is the conceptual thing about partial pressure? When I am writing that partial pressure of a gas A is equal to number of moles of that gas into RT divided by volume of the container. From this mathematical equation, I can write that the partial pressure of a gas depends, partial pressure of the gas depends, first point is that number of moles of that gas, right? It depends on, it is directly proportional to moles of gas. And second point is it depends on temperature and volume of the container. It depends on temperature and volume of the container. So if I am saying that I am going to add some inert gas into this gaseous mixture, the partial pressure of a gas is independent of the other gases, independent of the other gases present in the container, gases present in the container. So suppose I am saying that there are 3 gases A, B, C. If I am increasing the number of moles of gas A, there is increase in partial pressure of A, but there is no effect on the partial pressure of gas B and C, right? So it only depends on number of moles of that gas and temperature and volume of the container in which the gas is present. So let us solve an example based on Dalton's law. So in this example, there is a container which is separated by a semi-permeable membrane. This semi-permeable membrane is fixed, right? It is a fixed semi-permeable membrane. Now, The semi-permeable membrane separate this container into two parts. One is 10 liter, another is 8 liter. In one container there is hydrogen gas, in other container there is helium gas. Right? Now we can understand this point, like here there will be a piston, because when this semi-permeable membrane is there, the gas which can pass through this semi-permeable membrane will go from one container to another container. So we should understand that some thing is there, some mechanical piston is there which can be removed, and then we are talking about the process. So here we are saying that if simultaneously we are introducing 4 moles of hydrogen gas on the left hand side of the container and 4 moles of neon gas on the right hand side. So 4 moles of neon gas on the right hand side and 4 moles of hydrogen gas on the left hand side of the container. Then find the moles of hydrogen in container 1 and 2. Finally, if semi-permeable allows passage of hydrogen gas, I am in place of hydrogen, I am converting this into helium gas. What is the logic? If you study real gas, you know that the size of hydrogen molecule, right, the van der Waal constant B for hydrogen molecule is greater than the van der Waal constant B for helium gas molecule, because we know that what is B is representing the volume of 1 mole of gas molecules. So in helium there is only one atom, but in hydrogen there are two atoms. So the volume or the size of hydrogen molecule is greater than the size. So when we are talking logically, through this semi-permeable membrane, the pores of this semi-permeable membrane is such that the smaller gas particle can pass through it, and helium is smaller than hydrogen. That's why we are discussing this point. So that's why I have changed that helium gas will pass through this container. Now in order to solve this problem, we know that if a gas can move, it will always move from its higher pressure to lower pressure. So here we know that helium gas can pass, right? So helium gas will pass. So there is diffusion of helium gas from container 2 to container 1, right? And the concept of diffusion is based on difference in pressure. So finally, when this diffusion will stop, when we'll say that the partial pressure of helium gas in the first container is equal to the partial pressure of helium gas in the second container. In first and second container, the partial pressure of helium gas will be equal, then it is possible. So now, suppose we are saying that some amount of gases or of helium gas is passing from container 2 to container 1. Suppose the number of moles is A. So what is the number of moles of gas left behind? That will be 4 minus A. I am talking about in final condition when A moles of gas is here and 4 minus A moles of gas is here, so that the partial pressure of helium gas on the right hand side is equal to the partial pressure of helium gas on the left hand side. So from here I can write that the partial pressure of helium gas in container A is equal to number of moles of helium gas R into temperature divided by volume of the container. So the volume of the container is 10 liter. On the right hand side I can write that 4 minus A into RT divided by volume of the container, that is equal to 8 liter. Nothing is mentioned about temperature, so we are assuming that temperature in container 1 and 2 is equal. So this will cancel out. If I simplify this, I can write here also simplify 5 and 4 and then cross multiply. So we can write that 4 times of A is equal to 20 minus 5 times of A. So from here I can write that A is equal to 20 by 9. So this is the number of moles which of helium which will move from right hand side to left hand side. So what is the number of moles of helium left? So 4 minus A, that will be 16 divided by 9 moles, right? So through this example, what we have understood, one important point which is we should remember that about the size of hydrogen and helium molecule, that is an important point. The second point is about diffusion. When we are talking about movement of a gas, it will move from its higher pressure to lower pressure. So when the diffusion will stop, when the partial pressure or when the pressure of the gas on one container and other container become equal, then we'll say that the diffusion will stop, right? So this is an important point. When a gas is moving from its higher pressure to lower pressure, right, its diffusion will stop when the partial pressure of the gas on both sides will be equal. So these are the two important points regarding this question. Now practice one more. Again, this is a question based on Dalton's law. So in this question, they are saying that calculate the total number of moles of gases in each compartment after a very long time. After a very long time means they are talking about whatever the diffusion that is taking place when it is completed. Means partial pressure of the gas which is diffusing on one component and other side of the container will be same. Then we'll say that the diffusion is completed. So calculate the total number of moles of gas in each compartment after a very long time if the initial conditions is given below, right? So in this question, they're asking these things when we remove this piston. So there is a container which is divided in three compartments. The first compartment contains a movable piston and there is a mechanical stopper over here. So the question will start when we remove the mechanical stopper, right? So if we'll remove, we can see here that the volume of helium gas is less and here the volume is more and the number of moles are equal. So definitely the pressure of helium gas on the left hand side is greater than on the right hand side. So this piston will move in right direction, right? It will move on right hand side. And here it is mentioned that this is a fixed semi-permeable membrane, allow passage of helium gas only. So helium gas can pass from this container to that container, right? It only allows the passage of helium gas. So one thing about movable piston, we can say that a movable piston, and we are assuming that it is frictionless, there is no friction in this. So on a moving piston there is a pressure from both side, right? So at equilibrium condition, when we discuss that after a very long time when there is an equilibrium condition, we can say that the pressure of the gas on the left hand side, here it is helium gas, and the pressure of the gas from the right hand side on this piston will be equal. When these two will be equal, then only we can say that this piston will be in equilibrium condition, right? So this is important. For a movable piston, the piston will stop, it has a fixed position when the pressure on the left hand side and the right hand side will be equal. But the other thing is that when we are talking about a fixed membrane is like a wall, right? So it is fixed. So when something is fixed, the pressure on the left hand side and the pressure on the right hand side may be different, right? So suppose we are talking about two adjacent room and there is a wall, so we can say that in one room and the other room the pressures of the gases may be different, right? It is not necessary that the pressure on one side of the wall and the other side of the wall will be equal. But here, if a gas can pass from one container to another container, then the partial, like here helium can pass, so I can say that the partial pressure of helium on the left hand side and the partial pressure of helium on the right hand side of this fixed semi permeable membrane will, because this is diffusion, so diffusion will stop when the partial pressure of helium gas on both sides of this fixed semi-permeable membrane will be equal. So now if I, in this particular example, if I say that what is the total pressure on the right hand side of this semi-permeable membrane, that is pressure due to helium plus pressure due to hydrogen gas. While on the left hand side, the pressure, there is only pressure due to helium gas. And definitely these two pressures of helium gas on left hand side and right hand side will be equal. So in this particular example, in this fixed wall, I can say that the pressure or total pressure on the right hand side is more than the pressure on the left hand side, right? So in movable piston, this is not the condition. In movable piston, the pressures on both sides will be equal, but in a fixed wall, the pressures may be different. So that is an important point over here. So let us draw the diagram and discuss that what can happen in final conditions. So definitely this piston will move to the right hand side because the pressure is volume is less, so pressure will be more. So suppose it is moving on right hand side. So initially the length was 20 centimeter. Now the length becomes 20 plus x centimeter. This is a fixed semi-permeable membrane, so it is not going to move, right? So here what is happening, that due to movement of this, the length is going to decrease. So initially it was 40, now it will be 40 minus x, and this will remain same. On the right hand side it will remain because this is not moving, so it will remain 40 centimeter. And there is no change in number of moles of helium gas because it is a piston. It will not allow the movement of gas, so it will remain 10 mole only. Here, since helium gas can move, so suppose A moles of helium is moving. So what is the remaining moles of helium will be there? 10 minus A. This is the number of moles of helium. And hydrogen is not moving to the left hand side. So we can say that this is the number of moles of helium. And for hydrogen, the number of moles will remain same, 10 moles. Right? So this is the thing which is going to happen now. The pressure of helium gas on the left hand side of this piston and the right hand side of this piston will be equal. The partial pressure of helium gas in this second container and the partial pressure of the helium gas in this third container, if this is the first container, so partial pressure of helium gas in second and third will be same. So what I am saying, that for helium gas, the pressure of helium gas in the first container is equal to the pressure of helium gas in the second container is equal to the pressure of helium gas in the third container. So for helium gas, this relation is coming. Now if I am using the formula, because nothing is mentioned about temperature, assuming that temperature is same in all the three compartments. So now I can write that number of moles of helium will be 10. R into T. So let me write, then it will cancel out. nRT divided by volume. Volume should be, this is uniform cylinder, so area of cross section into length. That area will be common, that will cancel out. So just I'm writing in terms of length only. So that will be 20 plus x. For the second compartment, we can write here that is equal to number of moles 10 minus A into RT divided by length, that is 40 minus x. For the third compartment, we can write, for helium we are writing, so A moles of helium is there, into RT divided by length will be 40 centimeter, right? So here RT is common, that will be cancel out. So using this, because we can write, we can make some equations. So suppose if I'm using this first relation and third, because both are equal, from there I can write that okay, let me write 10 upon 20 plus x is equal to A upon 40. So if I simplify, that is equal to 400. 400 is equal to 20A plus AX. This is our first relation, right? Similarly, by using this second and third compartment, I can write again, let me write it, 10 minus A upon 40 minus x. 40 minus x is equal to A by 40. Again, simplify this. This is 400 minus 40A is equal to 40A minus 40x. Now we can simplify it further. We can write that 400 is equal to 80A minus 40x. So because there are two unknown, that's why I'm writing two equations, because from here third equation can also be written. So by using these two, 400, 400 in first and second, left hand side is equal. So we can equate right hand side. So 20a plus ax is equal to 80a minus 40x. Right? So from here we can write that a into x is equal to 60a 60a minus 40x. 60a minus 40x. Now we can okay, let me write the third equation also. It will be more easy if we write the third equation. So using first and second relation, I can write that 10 upon 20 plus x is equal to 10 minus a upon 40 minus x. So again, if I multiply, I am writing 400 minus 10x is equal to 200 is equal to 200 minus 20a plus 10x minus ax, right? So using these equation, this is the third equation. I think that using first and second equation, by using first and second, we can simplify it. So I think that on solving first and second, we are getting x is equal to 30. You check it, x is equal to 30. And we are getting a is equal to 8. Right? X is equal to 30 and a is equal to 8. So now the question was that what is the composition of the gases after final condition? Finally, what is the composition? So after diffusion, we can say that the value of a is equal to 8. So we can say that 2 moles of helium gas will remain in this container. 8 moles of helium gas will be in this container, and 10 moles of helium gas is present in the first container. So the number of moles of helium gas in the first container will remain same, but 8 moles of helium will present in the third container, and 2 moles of helium gas will be in the second container, right? So by using the concept of partial pressure, we have made these equation. On solving, these are simple equations. Also on solving these equations, we are getting that the value of x is what, and what is the number of moles of helium gas present in these three compartments. Okay, now we are going to discuss Graham's law of diffusion. So in Graham's law of diffusion, see, sometimes casually when you study your NCERT, they are using the word effusion and diffusion, right? So most of the time we are casually using the word effusion in place of diffusion, or diffusion in place of effusion. But there is a difference in effusion and diffusion, right? So diffusion is very common. So what is that diffusion? Suppose if I am saying that there are two containers, uh, they are connected by a negligible volume, pipe of negligible volume, right? So they are connected. Here A gas is there and here B gas is there. When we remove the stopcock, what will happen? That this A and B gas will intermix. A will move from container A to container B. Now A will be in both containers. A will present in both containers, and B is also present in both containers, right? So here mixing of gases is taking place. When this mixing of gases is taking place, there is a collision of A gas particle with B gas particle, right? This collision, already there is a collision between AA particle, right? There is a collision between BB particle, but now when this mixing is taking place, there is a collision between A and B particle also, right? So this is when we are talking about diffusion, this is related mixing of gases, that is diffusion. Like in kitchen, in order to know that our cylinder gas is has leakage or not, we are using a mercaptan gas, a smelling gas, right? And it is a lighter gas, it will move fast with respect to the other gases present in the that uh, cylinder, right? So that we able to find out that there is a leakage. So that is diffusion. Or when we are using scent, right? So when we enter into a room, right, after some time will the people in the room will observe the scent, right? So again, scent is an organic volatile compound, so it is diffusing through air. So this diffusion is very common. When we are talking about effusion, when we are talking about effusion, effusion is related with movement of a gas through a tiny hole in vacuum, right? So when a gas is moving from a container from a tiny hole in vacuum, then we are using the word effusion. Effusion. But if you follow NCRT, they are using the word effusion and diffusion casually, right? So unless and until they are not asking that what is the difference between effusion and diffusion, we'll assume that both are same, right? So now discuss that what are the factors on which a gas diffusion or effusion is going to depend. The diffusion or effusion of a gas will depend on what we are going to discuss. So suppose I'm saying that there is a gas inside it, so it has moles in the container. Volume of the container is V, temperature of the container is T, and it contains some number of moles N. And if I make a hole of cross sectional area A in this container, I can write what is diffusion, right? So when I am saying that what is rate of diffusion, first we understand what is rate of diffusion. Rate of diffusion. So I can write that this rate of diffusion is equal to the number of moles of gas moving outside the container with respect to time. So here minus sign is indicating that this change in number of moles is of the gas is decreasing with respect to time. Or I can write that this is change in pressure of the system with respect to time. Again the gas is going outside, so the pressure of the system is going to decrease with time. Or I can say, suppose if this is not a rigid container, suppose it is like a volume like a balloon, and there is a hole inside the balloon. So what will happen if there is a hole inside the balloon? The volume balloon will shrink, gas will go outside, and it will shrink. So I can also write that this is change in volume of the balloon with respect to time, right? Or I can say that rate of diffusion is if a gas is moving fast from this gas to outside, I can also write that the rate of diffusion is equal to the distance traveled by the gas per unit time. So I can also write distance traveled by the gas divided by time, right? Distance per unit time means speed, right? We are talking. So when we are talking about the rate of diffusion, the rate of diffusion can be represented in this four form, right? Now we discuss that what are the factors on which this rate of diffusion is going to depend. So the first factor, if I'm representing this rate of diffusion by R, I can say rate of diffusion is directly proportional to area of cross section of the hole. If the area will be more gas will go outside. I can say that if the if the container has more number of moles of the gas, means if the number of moles per unit volume of the gas will be more, rate of diffusion will be more, right? More gas particles is there, then their chances to go outside will be more. And the third factor is, we can say that if the particles are moving with larger speed, so it is also directly proportional to speed of the particle. For the system, suppose I am taking some particular type of a speed, average speed of the system, so I can say that the rate of diffusion is directly proportional to area of cross section, the rate of diffusion is directly proportional to number of particles per unit volume, or rate of diffusion is directly proportional to U average. So in a container, we can say that the number of moles per unit volume, PV, is equal to nRT. From there we can write, right, we are using the ideal gas equation, PV is equal to nRT. So N by V is equal to what? Pressure of the gas divided by RT. Similarly, we know that average speed of ideal gas particle is equal to under root 8 upon pi RT by M. So when we are discussing this diffusion, we are not changing the temperature or molar mass at a particular gas. When we write what are the factors on which it is going to depend, so rate of diffusion is directly proportional to area of the hole. Number of particles per unit volume can be written as partial pressure of the gas divided by RT. And average speed can be written as 8 by pi RT by M. So if we simplify this, we can say that rate of diffusion depends on four factors. One is area of cross section, other is partial pressure of the gas divided by here temperature and here temperature. If you simplify, both molar mass of the gas and temperature both will come in denominator, right? So here some student do mistake while writing that rate of diffusion is directly proportional to speed, and they are just considering the factor speed only. They are not considering number of particles per unit volume. So it depends on four factors. Rate of diffusion, on increasing temperature, rate of diffusion of a gas is going to decrease. If the gas is heavier, rate of diffusion will be less. If the gas has more partial pressure, rate of diffusion will be more, right? So this is an important relation. Now, what is the application of this rate of diffusion? So let us take an particular example. Suppose if I am saying that there is a gaseous mixture, and in this gaseous mixture there are two gases, A and B. So A gas is there and B gas is there. We are saying that A is a lighter gas, A is lighter gas, and B is heavier gas. So the molar mass of B will be more than the molar mass of A. So in this container, the number of moles of gas A will be Na, the number of moles of gas B will be Nb. So if I write that, what is the rate of diffusion of gas A with respect to gas B? So there is a gaseous mixture, and on opening the hole, the gas will come out. So we want to know that what is this rate of diffusion of gas A with respect to B. So here cross sectional area will be same for both gases, so this common factor will cancel out. Temperature of this container will be same for both the gases, so temperature will not come. So we can write that rate of diffusion of gas A upon rate of diffusion of gas B is equal to partial pressure of gas A, partial pressure of gas B, molar mass of gas B upon molar mass of gas A, molar mass of gas A, right? And we know that partial pressure is directly proportional to number of particles per unit volume. So I can also write here that is equal to moles of gas A, moles of gas B, molar mass of gas B upon molar mass of gas A. I can further simplify in terms of mass. Number of moles is equal to mass of gas A upon molar mass of gas B upon molar mass. So if I simplify again, it will come molar mass of gas B upon molar mass of gas A to the power 3 by 2, to the power 3 by 2. Rate of diffusion of gas A upon rate of diffusion of gas B. So we can write in different forms, right? We should know that it depends on four factors. Depending upon the condition, we can write that what is the formula. So most common questions is regarding the comparison of two gases present in the mixture. Sometimes they will ask a question in which they are comparing the diffusion of a gas with respect to a mixture. So suppose a gas is there and they are comparing this gas A with a mixture. So in that case, in place of molar mass, we have to write that what is the average molar mass of the mixture. What is the average molar mass of the mixture, right? So most of the question is based on that. And second application of Graham's law is in nuclear reactor, right? We know that uranium exists in two forms, uranium 235 and uranium 238. Uranium exists in uranium 235 and uranium 238. In nature, the element uranium is very less because it is a radioactive, right? And among these two, uranium 235 can be directly used in nuclear reactor. They can be directly used in nuclear reactor, right? Uranium 238 cannot be directly used. So in nature, whatever uranium exists, if we want to use the uranium in nuclear reactor, we should need uranium 235. So when we extract uranium, we have to separate uranium 235 from uranium 238. So what we do that, we convert the uranium existing in nature into uranium hexafluoride, which is a gas, right? Now this uranium hexafluoride is converted into a lighter gas and a heavier gas. If I am saying that uranium is 235, so mass number is 235, hexafluoride, we'll say this is a lighter gas with respect to uranium hexafluoride, in which uranium is 238. So it is a heavier gas. So now we know that if we see the formula of diffusion, a lighter gas can move fast with respect to heavier gas. Rate of diffusion is inversely proportional to molar mass, under root of molar mass. So lighter gas is moving faster than a heavier gas. So now I'm going to discuss that what is the method by which we separate uranium 238 from uranium 235. So a word is related that is known as enrichment factor. Enrichment factor. So the gas which is lighter, we are changing the composition of this gaseous mixture, and the amount of lighter gas with time is going to increase, right? So that is, the lighter gas is going to enrich. So that's why it is known as enrichment factor. So in order to understand enrichment factor, let us draw a diagram in which many containers are there. Initially in container 1, two gases, we are talking about two gases A and B. So the number of moles of gas A is N naught A, and the number of moles of gas B is equal to N naught B. So after the first step of diffusion, suppose there is a system where we can open this piston for some time, and there is a tiny hole in that, so that gas will move, and after some time we'll stop it. So after some time, some of the gases present in first container is moving into the second container. So after that time, we can write that this will be N1A and N1B. So again, we repeat the same thing. So after some time, what will happen after the second step of diffusion, in the third container will get N2A and N2B, right? Same way, third step. So after nth step, you can write what is the number of moles. So after nth step, I can write that the number of moles will be, let me write it capital N. So number of moles will be like this, capital N of B. So suppose I am saying that A is a lighter gas and B is heavier gas. A is lighter and B is heavier gas. So now if I compare, I can write after first step of diffusion. So I can write that rate of diffusion of gas A upon rate of diffusion of gas B. We are talking about the first step of diffusion, right? We are talking about the first step of diffusion is equal to, in terms of number of moles, I can write that is equal to N naught A upon N naught B. N naught B. All other factors will remain same, but molar mass is different. So we can write that molar mass of B upon molar mass of A. And we have studied that rate of diffusion can be represented in four forms, right? First, we have discussed this point only, that rate of diffusion can be written in terms of change in number of moles with respect to time. So here, if I am writing change in number of moles, means whatever the number of moles moving from the first container to the second container will be the N1A is the decrease in the number of moles in the first container. N1B is the decrease in number of moles of B in the first container. So after first step of diffusion, here I can write that this is equal to, time is same for both, so that will cancel out. So I can write that N1A upon N1B, that is equal to N naught A upon N naught B, N naught B, molar mass of B upon molar mass of A to the power half, right? So here there is a term known as separation factor. So separation factor in a single step, if I want to write that, what is separation factor in first step of diffusion or in a single step of diffusion? It means that what is the ratio of number of moles of A and B in the second container upon ratio of initial number of moles of A and B, N naught A and N naught B. So this is mole ratio after, so this is final number of moles, this is initial number of moles. So this is known as separation factor in a single step, and that is equal to molar mass of B upon molar mass of A to the power half. Same way, if I write that what is the rate of diffusion of gas A upon rate of diffusion of gas B in the second step. For the second step, I should write, because the gas is moving from the second container to the third container. So now I will write this is equal to N2A upon N2B, molar mass of B upon molar mass of A. And already we know that what is the value of, sorry, this will be N1A, because the gas is moving from the first container into second container, and this will be N1B. And already we know from here that what is N1A and N1B. So if I put this value over here, we can write N1A upon N1B. We can write that is equal to N naught A upon N naught B, molar mass of B upon molar mass of A to the power 2 by 2, because 2 times it is coming, so it is like that. In the left hand side, I can write that is equal to N2A upon N2B, N2B, right? So N2A upon N2B is equal to N naught A upon N naught B, molar mass of B upon molar mass of A. Number of effusion step will be 2 divided by 2. So in general, if I want to write after nth step, what will be the formula after nth step? So after nth step, I can write that rate of diffusion of gas A upon rate of diffusion of gas B after nth step is equal to initial number of moles of gas A, N naught A upon N naught B, molar mass of gas B upon molar mass of gas A to the power number of steps of diffusion divided by 2, right? And here I can write that is equal to number of moles of gas A after nth step, number of moles of gas B after nth step. So this is mole ratio of A and B after nth step. This is the initial number of moles ratio. Number of steps of diffusion divided by 2. So that is equal to molar mass of B, molar mass of gas A after nth step, number of moles of gas B after nth step. So this is mole ratio of A and B after nth step. This is the initial number of moles ratio. So that is equal to molar mass of B, molar mass. So now we understand the point that if the number of diffusion steps is equal to n, this is separation factor. If the number of diffusion steps is equal to 1, here in place of n we can put 1, right? So separation factor in a single step, separation factor after nth step. We understand the point that if the number of diffusion steps is equal to n, this is separation factor. If the number of diffusion steps is equal to 1, here in place of n we can put 1, right? So separation factor in a single step, separation factor after nth step. So let us discuss this point. There is a gaseous mixture containing two gases, hydrogen and deuterium gas. Suppose the mass of hydrogen and deuterium initially in the first container is W gram. So they have given composition by mass. So if I write that what is the mass of hydrogen gas? So let us discuss this point. There is a gaseous mixture containing two gases, hydrogen and deuterium gas. Suppose the mass of hydrogen and deuterium initially in the first container is W gram. So they have given composition by mass. So if I write that what is the mass of hydrogen gas? There is a gaseous mixture containing two gases, hydrogen and deuterium gas. Suppose the mass of hydrogen and deuterium initially in the first container is W gram. So they have given composition by mass. So if I write that what is the mass of hydrogen gas? In the final container, if the mass will be W dash, we know that as we are moving from the first container to the last container, this mass, if I compare the mass here, W will be more and definitely W dash will be less with respect to this W. But we are not talking about mass, we are talking about composition. So here again, if I write that container, if the mass will be W dash, we know that as we are moving from the first container to the last container, this mass, if I compare the mass here, W will be more and definitely W dash will be less with respect to this W. But we are not talking about mass, we are talking about composition. So here again, if I write that, so now again, if I apply the formula which we have derived, we can write that the number of moles of lighter gas, that is hydrogen, after nth step. So we should write number of moles of deuterium gas. Apply the formula which we have derived, we can write that the number of moles of lighter gas, that is hydrogen, after nth step. So we should write number of moles of deuterium gas. So molar mass of heavier gas deuterium upon molar mass of lighter gas hydrogen to the power. This number of moles can be written as mass upon molar mass. So it can be defined in terms of mass ratio, because number of moles upon molar mass in the numerator and denominator will cancel out. So if you write that what is the final mass, so final mass, if I write that W dash and 41 will be cancel out. In the numerator and denominator will cancel out. So if you write that what is the final mass, so final mass, if I write that W dash and 41 will be cancel out. So in this way we can solve the problem, right? Okay, in the next class, we'll further move forward to learn other topics. So in this way, we can solve the problem, right? Okay, in the next class, we'll further move forward to learn other topics. So in today class we learn about Dalton's law of partial pressure and Graham's law of diffusion. In Dalton's law of partial pressure, the gas mixture should be non-reacting gaseous mixture. It is valid for real gas as well as ideal gas. When we are talking about diffusion and effusion, so in today class we learn about Dalton's law of partial pressure and Graham's law of diffusion. In Dalton's law of partial pressure, the gas mixture should be non-reacting gaseous mixture. It is valid for real gas as well as ideal gas. When we are talking about diffusion and effusion, okay, in next class we are going to study about uh, payload of balloon, and we study about distribution of speed of ideal gas, right? So when you are sitting to see the lecture, please sit with pen and paper, right? So that if there is some important information, you can write it. Thank you. Bye. Take care.